Okay.
Welcome to Episode 2 of Programming Assembly Language for the Commodore 64 with ChatGPT. In this series, Mido will be using the Vice emulator to learn how to program in assembly language for the Commodore 64. I, ChatGPT, will be serving as Mido's guide and mentor, providing insight and guidance along the way. Let's get started and join Mido on this exciting journey of learning assembly language for the Commodore 64.
Okay. So. Okay, we're going to get the lesson plan for episode 3. Hey, sweet. She's going to try to have us do a sample program. That's cool. Okay. So. We'll do the first lesson and see what we get. She's talking about the memory map, it looks like. So probably useful to have that up while we have it read aloud.
Sure. The Commodore 64 has 64 kilobytes, or 64K, of memory. This memory is divided into several different areas, each of which is used for a specific purpose. The memory map of the Commodore 64 is as follows. $0000000FF 0 page. This area of memory is used for storing variables and data that are frequently accessed by the program. It is called the 0 page because the first byte of this area is located at memory location $0000.
Okay, so that's not even shown on the memory map we've got here, because the first address after 0000 is when we get to the A000. So, I wonder if it's like not a colloquial, but a standards of practice thing and not a hardware thing. But it does make sense that if the memory's not being used for anything else, I could definitely use the 00 through 00FF as an area to put variables specifically. That does sound handy.
$0.100.01FF stack. This area of memory is used for storing the stack. As the program executes, it pushes and pops data onto and off of the stack. $0.0200-$9FFF RAM. This area of memory is used for storing variables and data that the program uses during execution.
Okay. A to BFFF. So, yeah, okay, so this memory box, the one that is saying is basic, is apparently a good spot, or recommended spot to put graphics according to the AI. Okay, so then C block, which is that one, the third one, is where typically you see basic storing variables apparently. Now, interestingly, the C block on our thing here shows the color RAM. Or no, never mind. Okay. Yeah, okay, so the C block is just RAM. Then the D block, we have the color RAM taking up the latter half of it, it looks like. And then the first half could be I/O or character gen. Now, that actually conflicts with what she said here, with the I/O area being in the C block. This area of memory is used storing color information for the graphics displayed on the screen. And then E block is where you put the ROM. That specifically says the kernel, but it does clarify the kernel, so that was the memory management one. Okay. Sorry, I will not read in my head. That's probably really boring to see if anyone is watching this.
Sure, in episode 3, we will cover memory addressing modes in assembly language. Memory addressing refers to the way in which assembly language can access and manipulate memory locations in the computer's RAM. The two most commonly used addressing modes are absolute and relative addressing. Absolute addressing mode is used when the programmer knows the exact memory address of the location to be accessed. This is achieved by specifying the address directly in the instruction. Relative addressing mode is used when the programmer knows the offset from the current location of the program counter, which is the register that holds the address of the next instruction to be executed. The offset is specified in the instruction and is added to the value of the program counter to compute the memory address to be accessed. We will explore these concepts in more detail and demonstrate how to use them to access and manipulate data in memory. We will also discuss how the Commodore 64's memory is organized and the role of memory management in programming for the platform.
that actually all sounds like repeat information. So I'm a bit confused there.
A stack is a region of memory used for temporary storage. The stack grows downward in memory and is used to store return addresses, function arguments, and local variables. There are two main stack operations, pushing and popping. The push operation places a value onto the top of the stack, while the pop operation removes a value from the top of the stack. These operations are used to store and retrieve values on the stack. In the Commodore 64, the stack is located in the uppermost 256 bytes of memory, from addresses $0100 to $01FF. The stack pointer, which keeps track of the current top of the stack, is stored in the 6502 processor's registers. To push a value onto the stack, you can use the PHA, push accumulator, instruction to push the value of the accumulator register onto the stack. To pop a value from the stack, you can use the PLA, pull accumulator, instruction to pull the value from the top of the stack into the accumulator register.
Okay, so I really should be making notes of what we've learned as far as instructions go. So let's just create a notepad. So we've learned the STA, which is store contents of accumulator at given address. LDA, retrieve contents of given address into accumulator. So we have STA, LDA. We also learned something for moving into the X and into the Y from the A. I'll have to relook that stuff up. PHA, move contents of accumulator into stack, and what was the PLA? Move contents of stack into accumulator. Cool. There was also the jump, I guess we also learned for sure.
Stack operations are commonly used in function calls and interrupt handlers to store the return address and other state information on the stack.
Okay. So interrupts. Go ahead and stop, edit. Okay, so it's the same thing. Okay.
In computer systems, an interrupt is a signal sent to the processor indicating that an event has occurred that needs immediate attention. Interrupts can be generated by external devices, such as a keyboard or a printer, or by internal processes, such as a software interrupt. In assembly language programming, interrupts are used to handle events that occur during program execution. For example, the Commodore 64 has built-in interrupts for handling key presses, screen refreshes, and disk operations. By setting up interrupt handlers, you can write programs that respond to these events in real time.
Okay, so that's how, when making a game, you would receive the keystrokes to move the characters with that, because you don't want to be stopping the program to ask for the input. You want to just handle the input. And that's one thing that's always been a problem in my basic programs is I haven't really delved really deep in it. I've always just tried to create it myself. I haven't figured out a good way to handle input in basic. In a real-time fashion, I mean.
To use interrupts in your assembly language programs, you need to understand how they work and how to set them up. This involves understanding the interrupt vectors, which are memory locations that point to the interrupt handlers, and how to save and restore the processor state when an interrupt occurs.
Let's not do that. Let's try this.
In assembly language programming, interrupts are used to handle events that occur asynchronously with the main program execution. When an interrupt occurs, the processor temporarily stops executing the current program and jumps to a specific address in memory to execute an interrupt service routine, ISR. After the ISR is complete, the processor returns to the main program and continues execution. The Commodore 64 has two types of interrupts, maskable and non-maskable interrupts. Maskable interrupts can be disabled by the program, while non-maskable interrupts cannot be disabled. The most common use for interrupts in the Commodore 64 is to handle input-output operations, such as reading from the keyboard or writing to the screen. To use interrupts in your assembly language programs, you need to define an interrupt service routine and set up the interrupt vector table. The interrupt vector table is a table of addresses that the processor uses to jump to the correct ISR when an interrupt occurs. You can set up the interrupt vector table by writing addresses to specific memory locations. Once the interrupt vector table is set up, you can enable interrupts and the processor will automatically jump to the appropriate ISR when an interrupt occurs. Overall, interrupts are an important concept in assembly language programming, and can be used to add advanced functionality to your programs.
Alright, so it's still talking about the interrupts. So let's see, maybe advance to the next topic. So the next topic on the lesson plan. That right? No, actually, it specifically says that it's like introduction to memory management. That's weird. It's like it started over. Advance to the next topic on the lesson plan. Maybe because I didn't have it moving through topics to begin with. Graphics and sound programming. No, see, now we're at a totally different episode. No. So. So here's in it. Okay. So we're putting something into the accumulator. Cool. But it says that we're setting the stack pointer. I don't see how we're doing that. Okay, so we need to get that value into the X. Okay, I see. I see now what it's doing. Okay, the comment is for all three. So we load it into the accumulator. We move it from the accumulator into X. Then we move it from X into the stack pointer. There we go. Okay. Then we load 0 into the accumulator. And then store that 0 to D020 and D021. So we're loading 0 into both those things. Then we return from the subroutine, which loads up the message. Now that initially initiates the Y register to 0 with a LDY0 or LDY of 0. Which I think that's actually an address. So we're loading address 0 into it, I think. Or maybe it was that means X. I forget. Load the next character. So, okay. So as we progress, wait, no. Yeah, we're incrementing the Y here, but aren't we just going to keep resetting it every time? Or no, okay, because we've entered into a loop here, which we haven't learned loop. She didn't tell us about loop. In fact, I didn't know that there was a loop. I thought that you were supposed to use jump to simulate a loop. But if there's actually a loop, then there we go. Which, the loop thing might be something that the assembler has to handle. If we reach the end of the message, we're done. Okay, that makes sense. So, and it calls the kernel routine chur out. Okay, so there's already a way to output the character, I guess. Then we increment the Y register, then we loop back to load the next character. Oh, I see. So this is a label, is what it is. It's a label, separate from the message one, and then we're jumping to it. Yeah, so we're creating a false loop, like I was thinking. Well, not a false loop, but we're 100% controlling every aspect of the loop instead of the compiler doing it for us, I guess. Now, then done takes us to RTS, which brings us back up here, which also RTSs. So what is calling the start function then? Oh, it returns to basic. Okay, I see. Okay. And then now, from what I understand, I should be able to do this in Vice. From just having access to the monitor. But instead of writing it like this, we have to write each of the memory addresses for it. So, can you modify the example code to be entered at the monitor? Because we don't have a assembler set up. I was going to try to do this all through the monitor, so let's see if she can do it. Sweet! I don't understand what... Huh? There's no way that's the same code. It's way too short, right? Okay, I'll specifically ask for this program. So I'm gonna copy code, come down here, And then can you modify, because I don't know what it means, what it thinks I meant by example code. So let's go with that. Let's just, can you modify the code below? I'll say the code below to be entered at the monitor. And then we'll enter the code that we were given and say save and submit. Yes, you can enter the following code into the monitor prompt to assemble and run the program. Okay, but okay, so she at least new lined it for us. Wait. LDAY or LDY setting 0. That was done after message before, but now it's not. So where did that get moved to? Oh, here we go. I see. It's done up here at the top of the program. Okay, that makes sense. But this still isn't entered at the monitor because it doesn't have the memory addresses. What that example code just did. So let's try. This code does not have the memory addresses needed by the monitor. No, and then it reverted back. At the monitor, you need to have every line be formatted with starting with an A, then a memory address, then the op code, then the what was the term for the thing that you give to the op code? Then I'll just say value. Can you update the code to be written like this? Now, unfortunately, I have exterior information to know how to format the lines of code in the monitor. I was specifically told that. Ooh, this does not look right, though. Okay, I see what it's doing. So it's distilled each of the opcodes into its hexadecimal equivalent, I think. But then what's it done with the labels? Oh. And it still didn't do it right because it's supposed to be an A space. So, you know what? Let's just try to do this ourselves because, I mean, we just have to keep track of stuff, right? So, we'll go ahead and... Oh, wait, I can just... There we go, clear screen. So A space first memory address is 0001, and in there we're going to put an LDX for hashtag $00, right? Okay, and then it carries through for us. Okay, so we only have to enter the first one, I guess. Wait, what did it do here? 37. LDY hashtag $00 00. See, now that's different. And but it did knock us 2 forward. So I might have done something wrong in the first one. I can't run stop. Let's try that. Okay. Okay, so mon. Uh-oh. Of course, I know what I did there. Okay. There we go. So A, which we're doing at 0001. Let's try that. If I do that, okay. Now then it gives me that. LDX hashtag $00. No, okay, see, it's unhappy. Okay. So A0001 LDX hashtag $00, and it's unhappy about that. LDX hashtag $00. See, now that gave us an LDX. Okay, let's just advance the program. LDY. Okay, no. Okay, so I went and messed them up, clearly. So, okay, I think that... No, because you're able to enter the addresses. Yeah, I don't know. I think that I will... I'm going to look up how to get... I'm going to look up a different cartridge, because this cartridge doesn't have an assembler, is what I learned. I'll look up a cartridge that has an assembler built in, and then I will install that cartridge, and we will give a go at writing and running this code at the top of next episode before we move on to the actual episode itself. So this episode was a short one. It's only been about 40 minutes. But, yeah, we can't really move forward until I get this sorted, and I don't really want to do this with the stream going, because it's probably going to be a lot of me being an idiot. So I will catch y'all later. Have a great one.